Good afternoon, everybody. How you doing? Let's see, last time we were talking about some data that was a raster data. So these are raster files, raster layers in our GIS project. And we talked about, well, what exactly is a raster? It's this collection of pixels. Every pixel has a value, and that value corresponds to some physical feature, physical property, of the landscape at that point. Okay, so we're looking at this data from this vineyard out in California, near Monterey Bay, and let's pick it up where we left off. And so this is in chapter 9 in the textbook, and let's see if we can get through the rest of chapter 9 today. A little ambitious, but maybe we can do it. So if I go a little fast, if you have any questions, put them in the chat window, and I'll see them. Okay, so here we are. When we left off last time, we had these two raster layers, and oh, this doesn't look right. Shucks. Well, I guess I forgot to save. Awesome. So let me just make sure. We had one thing we did was converted. Shucks, everything we did last time is undone. All right, no deal, no problem. We can do it again. Let's see. So one thing we needed to do was to convert this feature to close that. There we go, feature to polygon, and we wanted to convert this. We did this last time. We converted the boundary of this property to a polygon. Oh, these things are all inside my let's remove that. They're all inside my geodatabase. They're just not on the desktop here, or on my project here. We masked out. So the next thing we did is we used the we had used this function, which is called extract by mask, and to crop out the part of these rasters that we don't need. So we're focusing on the area of these rasters that's inside the boundaries of this vineyard property, and so that's what we have right here. Let's change this symbology to something else, and then we can put it up on top, and then we can see the boundary. Okay, so the thing that we were doing last time was, well, we have these two rasters, and we want to stitch them together. So when you have more than one raster, it's called a mosaic, and we want to convert this mosaic into a new raster. So let me search for mosaic, and this is the tool we want: mosaic to new raster. So our input rasters are these two masked versions of the original, and we want to put the result raster into the same database. Here it is, vineyards.gdb, and let's call it something. Let's see, I'll use the naming that they use in the textbook, because, you know, why not? And they call it just NID property. Okay. So it's the entire property. And we're going to use the projected coordinate system of the property boundary. And the reason we're doing this is because the rasters here originally, they are only using geographic coordinate systems. So let's convert the coordinate system of this new raster layer we're going to create into this projected coordinate system, which is a universal transverse Mercator projection that's appropriate for this area of California. All right, and we'll leave the rest of the parameters with their default. Number of bands. We've got to say how many bands there are. There's just one band. It's just the grayscale pixel values between 0 and 255. Okay, it's running. And so now let's turn off these mask layers, and you see that we've accomplished what we were after. We stitched together those two rasters into one raster layer. That's now called NED property. Okay. So that concludes part A of chapter 9. 9A. 9B deals with the application of some tools which are used to perform operations on digital elevation models. So this data is bright pixels have higher values, dark pixels have lower values, and that corresponds to elevation. And so when you have a digital elevation model like this, where every pixel is a representative elevation, what you can do is you can use the information about a pixel and its neighbors to calculate things like slope, like how quickly is elevation changing. You could also calculate, we're going to calculate something called aspect, which is like if you put a bowling ball on a hill, it'll start rolling downhill, and whatever direction that is, that's aspect. So it's a compass direction, which corresponds to the direction of downhill slope. And the reason it's going to be important in this project is because the ultimate goal is to try to find a spot for a new field, a new planting for some new vines at this vineyard, and it's desirable to have land that has an aspect facing south. And that's because southward direction in the northern hemisphere gets more sunlight over the course of a day. Okay, and then we'll do one more tool which can apply to a digital elevation model. It's called Hillshade, and what this does is, I guess one way you can think about it is it creates a visualization of the landscape, like what it would look like if it was illuminated by the sun, a light source, which is usually the sun. So you can specify the azimuth angle, so that's the direction relative to north, compass bearing of the sun, and then also elevation in the sky, and it uses the information about elevation to figure out, well, what part of the landscapes will be shaded by hills and what part won't. So in the late afternoon, you'll get shading from the contours of the land. Okay. So let's apply these tools, and we'll look and see. We'll look at the results. Okay. Let's do the aspect tool first. So we'll go back here and we'll search for aspect. And the input raster is NED property, and we'll make the output, we'll just call the output aspect. And for the method, we'll keep it planar. Another option here is geodesic, but we've projected to a coordinate system, a projected coordinate system, which is appropriate for this area of the world. So the planar coordinates of locations on our map here are pretty true. There's very little distortion of our map, so that should be fine. And we'll run it. And so we get this wacky cool picture. And let me zoom in here a little bit. And what you're seeing here is that you look at the legend over here. The different colors correspond to different orientations, compass directions, if you will. North, northeast, east, southeast, south, southwest, west, northwest, and north. And I mean, you can see that these numbers, which range from 0 to 360 degrees, are azimuth angles relative to north. And so this is giving you, like right here in this region, most of this land has an aspect which is facing northeast. So the desirable thing here is you want aspect that is southernly directed, or southeast or southwest. So the blue colors, the greenish colors are good places to plant vines. Here we have northernly facing slopes. So those are not good for sunlight. The red color is not good. The gray color means it's pretty much flat land. So you see you got like these contours in here. And flat land is okay too for planting vines, apparently. Okay, so that's the output of the aspect tool. All right, it tells you, so it's just using just the information in the digital elevation model to figure this out. So next, let's use the slope tool. And again, our input raster is the combined property raster for the digital elevation model. And we'll make the output called slope. And let's see, output measurements. Our output measurements can be degree. There's another option here, percent rise. We'll do planar there, but let's set it to percent rise, and so that would be well, so what we should get then is a number between 0 and 100 if we're getting numbers in percent. Okay. Let's run this and take a look at the results. Okay. So the slope gives you, you got all these different values in the slope. Wow, some values apparently are over 100%, which is strange. Numerical problems, I suppose. But let's just mess with the symbology here a little bit, and we're going to do classify natural breaks, and let's just do two classes, and see. Well, let's not do natural breaks. Let's do manual intervals with 2 classes, and let's have one class represent values less than 14, and then the other class is everything else. So low numbers here mean, and this is a light color and this is a dark color. So low numbers here represent low slope. This is desirable in this analysis to try to find suitable fields for planting new vines. And the reason it's desirable is because apparently you want this field to be accessible to mechanical harvesting, and mechanical harvesters cannot operate well if you have too much slope in the landscape. So 14% rise is the limit of our analysis here. We want to find a location to plant the field that's at 14 or less in percent rise. All right. Okay, so so we again here are the areas where you have light color. Those are low slope areas, and the areas of dark color are high slope areas. So these areas of high slope are not desirable for planting. Turn that off. In the aspect raster, the areas that are blue or green, those are desirable. The areas that are orange and yellow and red, those are not desirable. They don't have the right direction. They don't face the southern sky very well. All right, next. The next tool we're going to use a couple times is called Hillshade. And let me pull up the tool here. And so what you got is an input raster. Okay, so the input's going to be our original NED property, the digital elevation model. And the output raster is, we're actually going to create 3 different output rasters here. So we'll call the first one Hillshade NED 1. And when I'm reading through the material in the text, what it's saying is let's perform this analysis for different times of day. So all in the afternoon or late afternoon. It's 2 p.m. and 2 p.m. 3 p.m. and 4:30 p.m. in mid-September. So the idea here is, later in the year, as you start going into the fall, the elevation of the sun starts to decrease. The peak elevation of the sun starts to decrease as you head toward the fall, and so that means that the sun's setting earlier, and it also means that if you have a physical landscape with lots of hills, you're going to get more shading earlier in the afternoon. So what's desirable here is to pick a spot that has a long growing season, which means that there's maximum sun exposure for the longest duration possible of the day. So you're going to use the Hillshade tool, and what you're going to do is you're going to program this tool to calculate what the shading of the landscape looks like at a specific time on a specific day. And the date that they picked for us is September 15th, so that's mid-September, and the times are 2 p.m., 3 p.m., and 4:30 p.m. Sure I'm getting that right. 2 p.m., 3 p.m., and 4:30 p.m. And so what we should see is that you'll have more shading at 3 p.m. than 2 p.m., and you'll have even more shading at 4:30 than you do at 3 p.m. But if we look at the tool, there we go. If we look at the tool, the inputs that are desired here are the azimuth and altitude of your light source, which is the sun. The thing that we need to know is, well, what is the azimuth and altitude of the sun at 2 p.m. on September 15th? And so in the textbook, they suggest a tool that you can use, a web tool, for figuring out what that is. Another thing that matters is where you are in the world. Obviously, if you're on the West Coast, the sun at a given time, the sun is at a different place than if you're on the East Coast. So you need a tool to figure out where the sun is going to be, and the textbook suggests a tool that is, I think it's the Navy. The Navy had created this tool, but actually this tool doesn't work anymore. I don't know why, but the tool doesn't work anymore. So we got to find a different tool, and that's not hard to do. Here, let me open up my web browser, and here we go. And so there's a tool which it's Global Monitoring Laboratory, Earth Systems Research Laboratory, is a division of NOAA, and it's called the NOAA Solar Calculator. Finds sunrise, sunset, solar noon. So solar noon is when the sun is has an azimuth of 180 degrees which means it's in the directly south. It will cast a shadow. This is actually interesting because I've used this when I was sighting solar panels, and I wanted them to have an aspect of south, 180 degrees, face south. And you can use a compass, and as long as you compensate for magnetic declination, you can use a compass, and that works great. But another way you can do this is you just gotta, okay, let's say it's July 1st. And you know what your latitude and longitude is. You put it into this calculator, and it calculates the time of day, which is called solar noon. Solar noon is not noon. It's not 12 p.m. Solar noon is the time of day when, at that latitude and longitude, the sun will cast a shadow that is along the north-south axis. And it's basically in the southern sky. And just a little aside there, it's an interesting and useful tool. Okay, but what you can actually do here is, here's Monterey Bay. This is Monterey Bay, and this vineyard is somewhere in this vicinity, and the textbook says it's near King City. So here's King City. What I did was I figured out what the latitude and longitude are of downtown King City, and I put them in to these boxes here for latitude and longitude for location. And then time zone, I just picked the city, Los Angeles, which is in the West Coast time zone. So that's minus 7 hours relative to UTC time, which is Greenwich time in Greenwich, England. And then you can put in the day, so that's the 15th of September, and the year, I picked 2020. Now in the textbook, they're probably not using 2020. Your answer was going to depend on this because, every 4 years we have a leap day, which tries to compensate for the fact that solar years aren't perfectly divisible by Earth days. And then local time. So if I put in 2 p.m. here, and then we see the calculated values down here, we get an azimuth angle. So at 2 p.m. September 15th in the year 2020, at this location, the sun has an azimuth of 206.07 degrees, so that's in the southwestern sky, and has an elevation of 53.6 degrees relative to horizontal. All right, so if I put those values, and these are a little bit different than the values, sorry, I forgot to change this back to sorry, I just realized I didn't have the right source on for you guys. All right, so just quickly, here's Monterey Bay, out in California. The location of this vineyard is somewhere near King City. So I looked up what the latitude and longitude are for this city, put it into the boxes here. I selected a time zone, which is West Coast in the United States, so Los Angeles. And then over here for the date, 15th of September in the year 2020 at 2 p.m. And when I do that, it calculates, the sun at that time of day, at this location on the planet, the sun is at 206 degrees, which is in the southwestern sky, and at an elevation of 53.6 degrees. Okay, so I'm going to put those into the boxes in this Hillshade tool for azimuth. And these are a little different than the values that are in the textbook, but it's not significant. So let me go back to the desktop. And I'm going to click Model Shadows. I want to model the shadows at this time of day with this azimuth and altitude, and I'll click Run. And there we go. So we see we got, quite a bit of shading up here, and not much shading over here. So now let me go back to the web browser and change the time of day to 3 p.m. and the azimuth and elevation change. The azimuth has increased, now it's further west, and the elevation has decreased. The sun is coming down. So I'll copy these. I'm going to come back here and I'm going to call this NED 2. And I'll run this, and so now we should see more shading, which we do. Compare that. So this is what shading looks like at 2 p.m. This is what it looks like at 3 p.m. Okay, so these are grayscale images, and you might say, well, something is either shaded or not shaded. So that it's not really calculating whether the sun is visible, is casting light on a spot versus not. It's also taking into account aspect and slope. It's calculating this grayscale value, which corresponds to how much, how intense the solar radiation is at that spot. So if you have a location that's flat, it's going to see more solar radiation than if it's, if the sun is in the western sky, southwestern sky. A piece of land that has an aspect that points southeast is not going to get as much sunlight as a piece of land that has an aspect that points southwest. So it's taking all of that into account. All right, so then we have one more to do. And this one is at 4:30 p.m. So we'll change the time to 4:30. And so now we get an even greater azimuth and an even lower elevation. The sun is setting, and we're going to put those in here and save that as NED 3. Hillshade NED 3. And we'll run that. And now we get even more shading. Okay. So as the day goes on, you get, so this is at 2 p.m., 3 p.m., 4:30 p.m. You get more shading. All right, so we now we have this material that's derivative now. We started out with the digital elevation model, and now we've used it to calculate these other raster layers. And we could turn on the so let me get rid of some of these layers. So these masked layers, we'll remove that. Remove this. NED 1, remove that. NED 2, remove that. So we have the aspect ratio, the slope, and the hillshades. Alright, and I'll get rid of the property boundary because we just want the property polygon. Okay, and then there's some other stuff in here we can add. We have vineyard blocks, put those on there. So these are the polygons representing the existing locations and extents of existing plantings, and then there's planting sites. So these are locations of potential planting sites, and let's visualize these a little different, just using black outlines, so that we can see if we can figure out where would be a good candidate site. So if we just start with the hillshade data and just look at the latest afternoon, I mean, this block up here looks pretty good. It's got less shading than this block here. This block has more shading, darker colors. This block has more shading. This block has less shading. Okay, so just looking at hillshade, that looks pretty good. Let's turn off Hillshade though, and let's look at slope. Well, again with slope, this potential plot here looks pretty good. It's got low slope. This plot right here, that's really bad. It's got really high slope. These plots have high slope too. These plots look pretty promising. Okay, turn off the slope, and now let's look at aspect ratio. Well, these plots, which look good when you looked at slope and hillshade, they don't look so good anymore when it comes to aspect, because they have a lot of red and a lot of orange. That's northern facing, and that's not good for this application. You think about, well, why is the shading good and the aspect not? Because shading is taking into account the position of the sun at a particular moment in time. And what we want is good exposure throughout the entire day. Long days, but good exposure throughout the entire day. And if you have northern facing slopes, that's less than ideal. This plot here, again, lots of oranges and yellows, not very good. This one, so this plot looks pretty good up here. It checks out in all of these categories, but oh, there's a plot over here too. This one looks, I didn't even see that one. Looks pretty good there. Oh, it's too slopey. It's too slopey. So you could sort of figure out, which plot is the best, just based on looking at the data and trying to figure out which of these potential plots is the best balance between these different properties. Which has the best aspect, which has the best slope, which has the lowest slope. In this case, is the best slope. Which has the best hillshade. All right, but that's sort of that's not very technical. So what we can do is we can try to figure out the best, the most suited site for planting these new vines by doing what's referred to as a weighted suitability analysis, a weighted calculation. So maybe slope is more important than aspect. So you could then weight the slope as like 50% importance and aspect as 20%, and then maybe what was the other one? Aspect, slope. Hillshade is the other 30%. So you could weight these things differently. So the thing is, well, you can't just start weighting things unless the things you are weighting have the same sort of range of values. And the way you can do this is you can do a new classification where you're saying you could pick a value in your data. So let's think of the slope data. We have this idea that a slope less than 14% is good, and a slope higher than 14% is bad. So what you can do is you could assign a value of 1 to all the pixels that have a slope less than 14, and a value of 0 to any pixels that have a slope above 14. And for hillshade, you can do the same thing. You see, like, well, there's a threshold for hillshade, and anything that is out of that threshold gets a 0. Anything that's achieves that threshold gets a 1. And then you can do the same with aspect. You can have some of these categories representing the aspect that's desirable, and you can code those pixels as 1s and all the other pixels as 0s. So that's the focus of the weighted suitability analysis, which is 9C. And let's see if we can get through most of this. And in 9C, to make this more interesting, what you're going to do is use the model builder to create a model to carry out these. First, you're going to reclassify the rasters, and then you're going to do a calculation on the rasters to figure out what the weighted sum of these things are. So we will go to the toolbox and let's search for reclassify, and I'm going to make 3 copies of this out here on my model builder, because we have 3 different, well actually more than 3, but we're just going to use the last Hillshade for this analysis. Okay, and so let's start with aspect. So I'm going to double click here, and the input raster here is going to be my aspect. And then you can see what pops up here are all the classifications in this layer. And you can assign new values to these classifications to reclassify things. And so what we'll do is, south is definitely desirable. So south is this category from 157.5 to 202. So we'll assign that a 1. Let's include south, east, and southwest as well. And we'll also include flat, okay, which is -1. And then everything else gets reclassified as a 0. Okay. Okay, so this will reclassify pixels that have values in these ranges as 1, and everything else will be reclassified as a 0. So I'll call this reclass. So this is a short. I'll just leave this default title. What the heck? It's reclassifying the aspect ratio data. So I'll click OK, and this will. And so we're passing the aspect raster data into this reclassify function, and we're getting an output. All right. It hasn't been generated yet. I haven't run this yet. I'm just building the model. And so here we'll do next. We'll do the slope. So we'll reclassify the slope. Anything less than 14 gets a 1. Everything greater than 14 gets a 0. And we'll save that as a new output called reclass slope. Okay. And then we'll use just the Hillshade 3 that we did, and we're going to reclassify the values here. And so we'll take values between 0 and 90 and make that 0. And then I hit enter to get another row, and anything that's between 91 and the max value in this data set, which should be, well, let's go over here. Let's take a look. So let's see, the min is 0, the max is 251. Okay, so we want to be able to classify values between there. And so we'll close that. And okay, oops, now I have too many. I'm going to delete that. Oops, I just erased everything. No problem, just put it back in. So numbers between 0 and 90 will get a 0. And then hit enter. And numbers between 91 and 251 will get a 1. And we'll call this reclass Hillshade 1. Okay, so our model builder now has this reclassify tool 3 times, and I'm reclassifying pixel values in the aspect raster, the slope raster, and the Hillshade raster to 0s and 1s using different criteria for these new classifications. Okay, so I could run this now and it would create 3 new layers in my map for these reclassified values, but I'm not quite done yet. So once I reclassify these values, I want to do the raster sum. So I'm looking for raster calculator right here, and I'll bring it out here. And if I double click on here, you'll see the options in here include, for the inputs, include these raster layers that haven't been created yet. The reclassified aspect, the reclassified slope, and the reclassified hillshade. So now I can build an equation which determines how the pixel values in these rasters will be weighted. And so I'll double click this. That didn't work right, hold on. Do you guys see this appearing and disappearing? So I'm double clicking. I want to operate on this raster. I want to multiply it by 20%. I want the aspect raster to count as 20%, the slope raster to count as 50%, and the hillshade to count as 30%. And you see it? Are you seeing it appear down here and then disappear real quickly? Maybe if I hand type it in. Why? Oh. Oh my gosh. All right. Well, something was wrong. So yeah, it just crashed on me. Great. So anyway, we'll pick this up on Friday. I don't know what was going on, but what we should see is that the so this is like a weighted sum is like what you do when you calculate grades. Exams are worth a certain percentage, projects are worth a certain percentage, and homework's worth a certain percentage, final exam. So you have individual grades in these different categories, and then you multiply by their weights and then add them together to get your total course grade. And so what we're doing here is exactly the same thing. The grade values, though, are pixel values. And so for a given pixel, there's a value in the hillshade, there's a value in the aspect, there's a value in the slope, and that value is either 0 or 1. And then you're multiplying those values by these weighting factors, 20%, 30%, 50%, adding the results together, and the result then is a new pixel value for a new derivative raster layer, which encapsulates information from all of these other layers. And so then the idea is, if that value is closer to 1, that location is more suitable for your planting of this new vineyard, these new vines, because it's going to be closer to 1 if the pixel values in the data that's going into it are close to 1. All right, so I got to recover ArcGIS, and we'll pick this up on Friday. I think I didn't save the whole time, so I got to redo all of that analysis. Awesome. All right, but it's a good time to stop. So I will see you guys tomorrow. Tomorrow, speaking of model builder, the lab tomorrow is all model builder. The idea is the analysis that you performed in chapter 6 in the project workbook. The question is, well, what if you need to do that analysis again? Well, what you're going to do is you're going to build a model of that analysis which chains together all of those processes that you did, and you'll create your own geoprocessing tool out of that model. And then if one of the parameters changes, you can rerun the entire analysis like that instead of having to go through it step by step. All right, so that's on tap for tomorrow.